Hi again everyone, Chris Tisdell here again. In this presentation I'm going to do a video that's connected with some of my recent research into mathematics. Now the nature of this video is pretty elementary, so don't be scared off when I say mathematical research. I'm very confident that a good student who's an undergraduate or even maybe a final year high school student will be able to follow quite a bit of what I'm going to talk about today. So the subject of this presentation is the following. I'm going to show you a problem involving a fractional differential equation, and I'm going to state and prove an idea called a comparison theorem, where you compare the solutions against each other to the problem. Okay, so let me share my screen with you and we can get underway. All right, so we're going to talk about special kinds of differential equations called fractional differential equations, and I'm going to prove what's known as a comparison theorem, where you compare two solutions using inequalities. Okay, so I'm just going to cut straight to the chase. Let's talk about some preliminaries. Well, we're going to introduce this rectangle here. Big B and little b are positive constants. So this is a rectangle that kind of sits in two-dimensional space, something like that. That might be B, in the middle is going to be A, and this thing here is going to be B. All right? And I mentioned fractional derivatives. What is a fractional derivative? Well, I'm glad you asked. I'm just going to talk about the case where the order is between 0 and 1. Yes, they do exist, and they're very old, and they're useful in all sorts of surprising situations. I'm going to talk about the Riemann-Liouville fractional differential operator of order Q by this big DQ, and it's defined by the following expression. Okay, so this is quite confronting if you haven't seen anything like this before. So let me just sort of break it down a bit. Okay, suppose you've got a function that you want to find the qth order derivative, where q is between 0 and 1. Okay, so you take that function, you multiply it by this t minus s to the negative q. You integrate the product with respect to s from 0 to t. And then you can multiply that by this constant where you've got the gamma function here. And then you differentiate the whole thing. Okay, now it looks a bit odd because you've got an integral and you've got a sort of a regular derivative here. Okay, but this is the way that this Riemann-Liouville derivative is defined. Okay, so I know it looks a bit weird. This is just a regular differential operator that you see at high school. Now, one interesting thing about this definition here is that because you've got fractional derivatives, some crazy things occur. Okay, so for example, if y is the constant function, the fractional derivative of a constant function is not necessarily 0. So that's a bit crazy, right? If you've got a little bit of time, I would invite you to just replace y of s with a constant k and work this out. You could do the integral first and then differentiate, and you will not get 0, which is crazy. Okay, anyway, moving right along. A so-called initial value problem for fractional differential equations is the following. Okay, you've got this dq acting on this left-hand side. You've got f over here, which is defined at least on this rectangle, and you've got an extra bit of information about the unknown function, the solution, at the point t equals 0. Okay, and it's common to assume that f is continuous. All right, so this is your basic basic fractional initial value problem, or IVP. Now, if q equals 1, let's say, this would just be like a dx dt or a x dash or something. This would disappear, and you've got the regular initial value problem that you see when you get to university maths. Okay? All right, so we've got a rectangle, we've got a Riemann-Liouville fractional derivative where q, the order's between 0 and 1, and you've got some sort of initial value problem. Okay, so let me introduce the main result just after this. A little bit of housekeeping. Okay, this is I don't want to get bogged down too much in this, right? But here are all the things that we mean when we talk about a solution, say to this problem here. Okay, so we call x of t a solution on some interval I if all of these things are satisfied. So 0 is in the interval, this thing's well defined, the graph of x lies in the rectangle, so the left-hand side's defined, the right-hand side's defined, and then this has to hold at all points, and this has to hold. So this is just ticking off these things. Okay, all right, so I don't want to get bogged down too much in that. Okay, so here is the result that I want to talk about in a bit of detail. Okay, all right. So it's called a comparison theorem. All right, so suppose W is a function that is defined on a rectangle like this. It's a function of two variables, okay? And it satisfies this condition here, which is a famous condition called a Lipschitz condition. So there is some positive number L such that this is less than or equal to this for all pairs of points in the rectangle. Okay, so that's the first assumption. W, we don't know what it is, but it satisfies the Lipschitz condition. In addition, let x be a function that satisfies this kind of problem. Now, notice I've got an inequality here. Okay, so instead of having equality, I've got an inequality here. All right, so this is what's known as a differential inequality. Okay, so let x satisfy this kind of initial value problem where you've got an inequality instead of an equal sign, and let y actually satisfy the problem when you have an equal sign here. Oh, okay, hang on, I just need to restart the document camera. Let me just see if we can get that going again. Okay, I might just need to restart the document camera. Just give me a second. Okay, so at the moment, I'm just introducing three conditions in this theorem, this comparison theorem. One is a Lipschitz condition, one is an inequality involving x, and one is y satisfying an equality. All right, here we go, we're back again. Okay, hopefully it doesn't crash again. All right, so we assume this, this, and this, and also this number is less than or equal to this number. Then, and this is the big conclusion is that the function x satisfying this and the function y satisfying this can be compared. And in particular, the graph of x stays below the graph of y on the interval I. Okay, oops, yep, all right, so that's it. That we're comparing x with y, where x satisfies this, y satisfies this, and w satisfies a Lipschitz condition. So let's go through and see if we can prove that. Okay. All right. So what we're going to do is sort of argue by contradiction. We're going to assume that there is a point in I such that this doesn't hold. This inequality doesn't hold. And we'll show that you end up with a whole bunch of nonsense if this isn't true. Okay? So let's assume there's a point T1 in the interval, which I've defined to be that, such that our conclusion of the theorem doesn't hold. Okay, what we're going to do is show that this actually leads to some sort of nonsense. All right, so let's introduce a function r, which is just the difference x minus y. Let's look at what this means for r. Well, this means that r of t1 is positive. And this assumption, which is x of naught is less than or equal to y of naught, means that r of naught has to be less than or equal to 0. Okay, so this is going to be important in a minute. All right, so let's let t naught be the greatest value in this interval I, such that r of t naught equals 0. So if I just sort of draw a little graph here, here's r and here's t. I know that r of 0 is less than or equal to 0. Let's say it's there. And I've assumed that there's a point where r of t1 is greater than 0. And, because these things are continuous, there's got to be some sort of last point t0, or greatest point t0, where r of t0 is 0, okay? All right, so for all points in that interval t0 to t1, we have r of t is greater than or equal to 0, with r of t being strictly greater than 0 on the sort of half-open interval, if you like. Okay. All right, well, we know that this is 0, right? So let's talk about taking the fractional derivative of order q of r of r minus t0. Okay, well, that's just 0, so that you can just cover that up, really, if you want to. Okay, well, r is this here. So you can break that derivative up. It's a linear operator, and you can have it write it like this. Now, if you then plug in this condition and this condition, condition 3 and condition 4, you can form this inequality to go from here to here. And because we've assumed a Lipschitz condition too, you can go from here to here. Now, notice there's no absolute values in here, and there are absolute values here. Why is that? Well, it's because x minus y is positive on that interval, so you don't need the absolute value signs. Okay, so these are like, these are not necessarily absolute value signs. Okay, so we end up with the following. This is another fractional differential inequality. It's dq of r is less than or equal to LR, okay? Because x minus y, that's how we defined r. So and that's 0. So dqr is less than or equal to L of r. And we also have an initial condition, r of t0 equals 0, because that's where it passes through the horizontal axis. Okay, this is a special inequality called a linear fractional differential inequality. Okay, now in previous videos, I've shown how you can recast this problem in this integral form. Okay, or you can look it up in my paper, which is reference 2 in the in the references, which I'll show you. Okay. Now, from that, or equivalently that, these two are the same kinds of problems. You can apply a special inequality called Gronwall's inequality. And yes, I have a video about that too. Okay, or you can see it in my reference too. So for each function R that satisfies this, or equivalently this, it can't be positive. It's got to be non-negative on the interval of interest. Okay, so now we've reached a very critical point in the proof. Okay, we saw that R of t had to be positive on this interval. And what have we just shown? We've just shown that R is non-positive on this interval. So you can see this says, oh, R's positive on this interval. This says, oh no, hang on, R can't be positive on that interval. So there's your contradiction. We showed, oh yeah, R's got to satisfy this, but R has to satisfy a totally incompatible other inequality. So there's your contradiction. Okay, this contradicts this thing. So what can we conclude now? Well, we know that this cannot be true. There cannot be a point in the interval such that that holds. So what does that mean? It means that we must have this inequality holding. Okay? All right. All right, well, that is the little comparison theorem that I thought I'd share with you. Here are a couple of papers. This is one of mine, which contains some of the Gronwall's inequality and things like this. This is also a very important seminal paper, one of the early ones. So let's just recap the theorem again. Suppose W is a function that's defined on a rectangle, something like this. W satisfies a Lipschitz condition. X satisfies an initial value problem like this, where you have an inequality, not necessarily an equality. Y satisfies your sort of standard initial value problem for fractional differential equations. And the two initial conditions satisfy this inequality. Under those assumptions, you can compare the solution to this with the solution to this through this inequality. X has got to be less than or equal to Y on the interval of interest. Okay, so that's my research presentation. Hope you enjoyed it. Hope you found it useful. As you can see, research is not, it doesn't have to be wildly abstract, although, you know, truth be told, the idea of a fractional derivative kind of freaks people out when they first see it. So thanks for watching. If you have any feedback, any comments, I'd love to hear them. You can always post a comment in the comments section. So in forthcoming videos, I'll be continuing some more of these research type presentations. Let me know what you think. All right, thanks for watching. Bye.